In this clip I'll show by means of a simple example how Bayesian estimation works. It's an extremely simple, perhaps even the simplest possible example. The question we're going to tackle is there a positive trend in global temperatures? And we will look at data from the climate research unit at the University of East Anglia, and the data set is here, HATCRAT for global temperatures. If you search for this, you will find the data and you can get more details. This is what it looks like. They are centered around zero approximately because they're not temperatures per se, they are temperature deviations. The way we start is by defining a variable yt, and that yt will equal to 1 if the global temperature from one year, from year t-1 to year t, increases. Okay, so ones in yt indicate temperature increases, zeros otherwise if the temperature doesn't increase. Now let's propose a very simple model, a binomial model. We'll say that the probability of yt being equal to 1 is pi, and therefore the probability of yt being equal to 0 is 1 minus pi. Okay, we can write this down as a likelihood function. Right? That will look familiar from maximum likelihood estimations. So we'll say the probability for yt conditional on pi is pi, and the probability for yt equals 0 conditional on pi is 1 minus pi. And that's the form in which we'll soon need it. Now that pi, this is of course unknown. Okay, it's an unknown parameter. And now if you also treat it as a random variable, that will be the influence of Bayesian thinking. Frequentists wouldn't look at it as a random variable, and what we want is the distribution of pi conditional on y, the data. In order to find it, we will use the following very basic probability relationships. The probability of pi conditional on y is equal to the probability of y conditional on pi times the probability of pi divided by the probability of y. So what are all these things we're looking at here? Now what we already know is this one here, probability of y conditional on pi. This is just our likelihood function. This is what will be called the prior distribution. This one here will be called the posterior distribution of pi, and this one is what is called the marginal distribution of y, so of the data. As this distribution does not depend on the parameter we are interested in, on pi, we will actually somewhat ignore it for this purpose. So we will write down the posterior distribution is proportional, that's what this sign means, to the likelihood times the prior. So when we calculate that, we're not actually getting the posterior, we're getting something different because we've ignored the marginal distribution of the data. So therefore I call that pp, just to give it a different name, and eventually it will need some rescaling or standardization such that it's a distribution again, meaning all probabilities sum up to 1. So consider now that we allow the following values for pi I. I'm going to discretize the problem: 0, 0.01, 0.02, all the way to 1. So altogether I have 101 values. So I'm thinking of pi as a discrete distribution, although clearly this is an approximation, it's really continuous, but this will simplify the calculations. What prior do we use? Let's say we use the uniform prior. That means the probability for each of these values is 1.101. It's an uninformative. What about the likelihood? We already have that up here. We had said that the probability of y equals 1 is just pi. It's binomial type random variable. I can write this down in a very general form, regardless of what value yt we have. We can say probability is pi I times yt. So if yt is equal to 1, that will be pi I plus 1 minus pi I times 1 minus yt. And you can see that yt and 1 minus yt term, this will switch off one of the two summands depending on what value yt is. Let's present the first observation to our algorithm. Okay, so let's look at the data. Here in the variable diff, I calculate the temperature differences. Ups will be 1 if the difference is positive, and if I look at ups, the first value is actually a 1. So in the first year we have an increase in temperature. Now we want to figure out what sort of calculations we need to do to get this posterior distribution conditional on the first observation. So we need to undertake calculations for all possible values of pi, so from 0 to 1. And what do we need for each of these values? We need to know what the likelihood is, the probability of yt given that particular pi I, then the prior probability pi I, and that shall give us the posterior. The easiest is the prior, because at the first stage this is 1 over 101 always. Then at the likelihood, now since our observation is 1, that second part will fall away, so it's just pi I times 1, so it's just pi I, so we just need to copy our pi i's across here. That's a feature of our very simple model. Often this will be much more complicated, may involve several coefficients indeed. We can do all these calculations. This is all just doing a bit of algebra, 0, the first one, and so forth. The fact that the first one is 0 makes sense, because that would say the probability of having an increase is nil. It's impossible, but we had an increase, so that's impossible, and therefore we now have a 0 there. Now if you add up all of these values you get 1, but if you add up all the posteriors you get a value smaller than 1. Now in the code I want to show you that p-val, that is our vector of all the possible values of pi. Okay, so now it's the p-val vector. Now our prior distribution is just 1 over the size, that's 101, so 1 over 101. Then here is where we do the updating. This is where we put our pp in. I should have called it pp. Okay, we start out with zeros. Then we have a loop over all possible values of pi. That's over 101 values. Here we now have on the right hand side the likelihood function times the prior. So first the prior, and then the second bit in each of the sums, this and this, is the likelihood function. And it's in the form of pi val times y and 1 minus pi times 1 minus y, as exactly as we've written it down here. Okay, and we go through all this loop, and then we have a vector p joint 3. We calculate the sum of this, and then we do the standardization. Then we divide each value in p joint 3 with that sum, which is p tick 3, and what we get is fp post 3. Okay, p tick 3 is the sum of all the pp values, and what we get f post, this will then be put into the prior. So for the next observation for y2, our posterior, which we just calculated, will be the prior, and that will not be 1 over 101 anymore, as you've seen in our table. So what else did I want to show you here? So that means the calculations we've done in our table are all done in the code. So let's run this and see what happens. We should see, here we go. Yes, you can see in the lower bit, you can see the posterior distributions, and with every additional value of y, they are changing. Okay, and we're now running quickly through all the observations, and now we have updated everything, and you can see there's considerable difference between the priors and the posteriors, and the posteriors also differ considerably with the priors. Okay, so what prior you have really matters. So you can see there's a wide range, so even the uniform, there's a wide range of probability. It's difficult to say where the true pi is, the true probability. Now, what would we actually do in practice? Especially I want to briefly talk about how we would get priors. We have data from 1850 to 2030. Now at the beginning nobody cared about climate change. Now it's possibly in 1972 when a book was published. That book was called The Limits to Growth. Here it is, the limits to growth. That was published by an organization called the Club of Rome. This still exists, possibly has less influence these days, but then this book talked about the limits of an exponentially growing economy, and it was possibly the first time that people worried about limits of resources. Now what we're going to do is we're going to use the information up to 1972 to obtain a prior, and then the observations from 1973 onwards we're going to use to update this prior. So to get a prior, what I do is the following. The 124th observation is observation in 1973. So what I'm going to do now is I'm going to calculate the mean of YT, and therefore the proportion of increases in global temperature up to 1972. So in this software which I use, you don't really need to know this. I do that by using mean apps 1 to 1, 2, 3. Okay. The mean of these observations is about 0.5, pretty close to 0.5, so let's use 0.5. So let's use this information to propose a prior. This is really a little bit of frequentist view coming in here, but you can get the prior from wherever you want. I propose that pi's prior is a normal distribution with mean 0.5, and the variance as we would calculate it if we were calculating the variance of pi hat. And then I'll use this information and I'll plug it here into the prior. So I'll change this. This is going to be our prior mean. The standard deviation is going to be the square root of our variance formula. So what we use is the estimate times 1 minus the estimate over the number of observations. As I said, that would be the variance for pi hat if you were a frequentist. And everything else will remain unchanged. No, I need to now restrict the data from 1 to 4 to end. Okay, so now I'm only updating from 1973 onwards. I'm basically ignoring all the data previously. That information has gone into the prior. And now let me just start. In the end, we're going to look at the posterior probability just for prior 1. Let me also comment out the graphs for prior 2 and prior 3. Again, just ignore. Don't need to understand what exactly I'm doing here. Okay, save it and we'll start. Let's see where we get to. So here we go. Here's our new posterior, starting from our new prior, updating from 1973 to 2013, and here's the posterior distribution we get. And let's look at the probability we get from that pi is larger than 0.5. It's 0.7261. So what is that? Here's the posterior distribution using the prior you can see in the top left corner here, updated over the data from 1973 to 2013, and the probability that P or pi is larger than 0.5 is 0.7 or about 0.73. And what was that probability? That's the probability of what was the pi? That's the probability of getting an increase in the global temperature from one year to the next. Right, so we would put a quite large probability of there being a positive trend, but there's also a sizable probability, about 27%, that pi may be smaller than 5. So it's not conclusive evidence for increasing global temperatures by itself. But of course, we've only used a tiny bit of information here, some temperature data. Climate science does much more than that. For instance, importantly, we understand the science behind, or the link between CO2 emissions, for instance, and temperature change. That's incredibly important. But what this was a demonstration of how we would use Bayesian estimation methods to estimate a parameter. This was a very simple model. It only used one parameter. If you have models with several parameters, these complications become much more difficult, and usually you cannot use any standard software. So here I used MATLAB, but you would really need to know how to integrate distributions. We're not going to do this here. It was really only to convey the main ideas of Bayesian estimation.